All right, I was about to say that I'm choosing the equation for block 2 because it's a little shorter. In either case, I need to know the force of kinetic friction on one or the other block in order to solve the problem. So I know the acceleration is 1.764. I'm going to use my version and not the textbook's solution. And I need to know that kinetic friction on block 2 is equal to mu sub k times the normal force on block 2. So I can't use the kinetic friction I found in part A. This 0.18 times 190 times 9.8 would be the kinetic friction on the sort of imaginary mega block. Instead, I have to do 0.18 times block 2's mass, 125 kilograms, times 9.8 meters per second squared. I'm totally running out of room there on the page, but imagine that's 9.8 meters per second squared. And so that force of kinetic friction on block 2, just by itself, 0.18 times 125 times 9.8 is 220. Okay, 220.5. So that's here. And mass 2 is 125. So I'm solving for the force of block 1 on 2, which is the same as the force of block 2 on 1. They're equal and opposite action-reaction. So once I know one, I know the other. And so the rest is algebra. And so you will find, according to solution, that the force between the two blocks, 1 on 2 or 2 on 1, is hopefully 430 newtons. I'm going to skip reporting myself actually calculating because hopefully you know, well, you need to know how to use a calculator by now. We could also have solved the problem from this stage altogether, noticing that this pair of free body diagrams gives us a pair of equations with a pair of unknowns, right? We didn't know the force between the blocks, but these are equal and opposite action-reaction forces. And then we also didn't know the acceleration at part A. So we could have solved the system of two equations and two unknowns from the start to answer the problem, or we could have answered the acceleration part like we did, considering a mega block consisting of the pair of blocks. Now, part C asks us to repeat this problem with the crates reversed. So for part C, we don't need to do anything to change the acceleration. The acceleration of the pair of blocks, whether that's block 1 first and block 2 second, or block 2 first and block 1 second, whether it's 65, 125, or 125, 65, you still have a block of total mass 190. You still have the same friction, and so you still have an acceleration of 1.764 meters per second squared. The difference now is in the free body diagram. So in the free body diagram of 2 pushing on 1, we do have difference. 1, or rather, I'm going to keep calling this 2, and this one 1, 125, and 65, because now the 650 Newton force is exerted on the 125 kilogram block. Here, and so we have different free body diagrams. 2 has a free body diagram, normal force 2, pull of gravity 2, those are the same as before. We have 650 here, we have the pushback of 1 on 2, and we have friction. We have the same acceleration, right? We have to have the same acceleration of 1.764 meters per second squared, but we have a different series of forces acting on block 2. So I don't even think we need to look at the free body diagram for 1, or maybe we should, but we don't need to do any calculations for block 1. We just need to look at the fact that we have the same acceleration and different forces acting on these blocks, FK1, to find the new force between the two blocks. And then once again, as I can see, I've lost my focus here. Once again, choose the easier one, right? We've already calculated, oh wait, no, it's not easier, because we already calculated the force of kinetic friction on block 2. We know that from before, 220.5 newtons, right? Mu sub k times normal force. We know 650 And so we know the acceleration is still the same by my mass. So acceleration is 1.764 meters per second squared. And then we have 650 to the right. We have 220 friction, 220.5 to the left. And then we have F12 to the left, all divided by 125 kilograms. And so we multiply both sides by 125. I'll go ahead and show the algebra for this one. So both sides by 125. So I've got 1.764 times 125. So my left side is, oh, that's odd. Wait, really? I think I just made an error in my calculation. 1.764. Nope, 220.5 is equal to 650 minus 220.5 minus F12. And so I have, no, this will be okay. So 650 minus 220.5, 429. Okay, so on the left side, I end up with negative 209 equal to negative F12. So the force from block 1 on 2 or block 2 on 1 is 209 newtons. When I push the other direction. Oh, that's interesting. Okay, either I've made a mistake in my calculation or there's a mistake in the solution. I'm actually seeing a mistake in the solution, or a difference in the solution. So the solution says that part C, acceleration, they agree, is 1.7. You'll see in the solution, though, that they use an acceleration of 1.657 meters per second squared instead of the 1.7 meters per second squared. So there's no explanation as to why they suddenly use a different acceleration after stating that the acceleration is the same. And it's, once again, we're not surprised by weirdness in the solution given for this textbook. But in any case, the process is correct. Using the calculated acceleration I have for part A, which is 1.764, we are finding that the new force between block 1 and 2, 2 on 1, is 209 rather than 430 when I was pushing the smaller block with the 650 newtons of force. So order does matter in terms of the internal force, but the resulting acceleration is the same either way.